Welcome to Classes with Atish. Today we will continue with what we learned a little bit about mole concept and its application in stoichiometry. So we'll specifically focus this lecture on stoichiometry. So let's start. Let's look at a very simple chemical reaction. Hydrogen combining with nitrogen to give ammonia. This is a reversible reaction. Okay. This chemical equation is not balanced. We will need to balance it first. But let's little bit dwell deep into what's happening here. Okay. So hydrogen molecules combining with nitrogen molecules to give ammonia. But you can see that there are two hydrogen on the left side, only three on the right side. Similarly, two nitrogen on the left side and one nitrogen on the right side. So what we first need to do is balance this equation so we have equal number of atoms on the both sides, right? How can we do that? So if we do a 2 here, so there is 2 nitrogen here, 2 nitrogen, nitrogen is balanced, but there is 6 hydrogen on the right side, so we put a 3 here, so then there is a 6 hydrogen on the left side, so now this is balanced. Now once this chemical equation is balanced, what does this signify? What this signifies is, it signifies 3 molecules of hydrogen gas, H2 gas, combines with 1 molecule of nitrogen gas to form 2 molecules of ammonia. Okay? Now, what does molecule signify? This is number of particles that are combining. Now, stoichiometry gives us the ratio, the relationship of number of individual reactant substances combining together to form individual product substances on the right side. Okay, so this 3 molecules, it is very difficult to actually see 3 molecules combining with 1 molecule to form 2 molecules. It's very difficult to observe, it's very difficult to measure that. So to convert this into a measurable quantity, we actually look at a bigger number of molecules. Now how many molecules should we look at? 3,000, 3 million? So what we have found out is, if we look at Avogadro number of molecules, remember we introduced Avogadro number in our mole concept class, it's equal to 6.022 into 10 to the power 23 numbers of molecules, say in this example. If we consider Avogadro number of molecules, then it all becomes a measurable part. Why? Because Avogadro number of hydrogen molecules is what? So this can be converted into 3 moles, right? So which is nothing but 3 times Avogadro number of molecules. Remember, mole is just a number. Similarly, this gets converted into 1 mole, which is 1 times Avogadro number of molecules, and this gets converted into 2 moles, okay, which is 2 times Avogadro number of molecules. So far we have been dealing with numbers. Now what's the advantage of using moles and not molecules? Now these can be measured, right? So we know 1 molar mass or molar mass of hydrogen is how much? There are 2 atoms of hydrogen, so 2 grams. Now that is a measurable quantity. Now how many moles are there in Avogadro number of molecules? 1 mole. So if there are 3 moles of hydrogen molecules, so how much is this? 3 times molar mass, which is 6 grams. Okay. Similarly, molar mass of nitrogen gas is 14 times 2, 28 grams. So when we say 1 mole of nitrogen gas it means there is 28 grams of nitrogen gas. Similarly, molar mass of ammonia is how much? It is 14 plus 3, 17 grams. Now there are 2 moles of ammonia, so it is 34 grams. The ratio in which the molecules combine is the number of molecules or number of moles. So the thing to remember here is these coefficients. When there is no coefficient, it means 1. These coefficients represent number of moles or number of molecules that are combining. It is not representative of the mass of individual substances that are combining. Okay? So the key here is to solving these type of problems in stoichiometry, you will have 3 types of problems. Mass to mass problems. Like for example, they will ask you 6 gram of hydrogen is combining with nitrogen gas to form how many grams of ammonia. So those are mass to mass problems. Then you will have mass to mole problems. Okay, so which means they will ask 6 gram of hydrogen is combining with X gram of nitrogen to form how many moles of ammonia. Then you might have moles to moles. This is straightforward. This can be easily obtained right from the equation, the balanced equation. And the last one will be moles to mass. Okay? So this is where we start from. This is the easiest. Start from here. Okay? Because this you can obtain from the balanced equation. Okay? So start with number of moles. So here we can infer 3 moles of hydrogen combines with 1 mole of nitrogen to form 2 moles of ammonia. Then you convert moles to mass using what? Using a formula that we had introduced previously. Total number of moles is total mass divided by molar mass. Okay. There is another formula which is applicable only to ideal gases and at STP. That is total moles equals total volume, because we are dealing with gases here, divided by 22.4 liter. This 22.4 liter is what? This is molar volume at STP. And this applies only to ideal gases. Okay. So these are the 2 formulas that we are going to use to convert moles to mass, mass to moles. Okay. And then if you are able to do that, then you can work out these 2 problems easily. And then if you convert both sides moles to masses, then you can also solve the mass to mass problems. Okay. So with that background, let's solve some problems. 20 gram of propane combines with oxygen. So let's say C3H8 is propane, combines with oxygen to form carbon dioxide and water. Okay. Find volume of oxygen needed at STP for complete combustion. B. Mass of H2O produced. Okay. C. Number of moles of oxygen atoms in carbon dioxide produced? Okay. Question number 2. 50 gram of calcium carbonate is heated. Okay. Now, calcium carbonate, CaCO3, when heated, it forms calcium oxide and carbon dioxide. Okay. Find volume of carbon dioxide produced at STP. Third question. Consider this reaction: calcium nitrate is heated to form calcium oxide, nitrogen dioxide and oxygen. If 5.6 liter of nitrogen dioxide is produced at STP, what was mass of calcium nitrate that was heated? Okay. Okay, so the first question. So first thing is, let's balance this equation first. C3H8 propane combining with oxygen giving carbon dioxide and water. Okay. So there are 3 carbon, 8 hydrogen here. So if I put a 3 here, so there is 3 carbon is balanced, but there are 6 oxygen and 7 oxygen. It will be difficult to balance here 7 oxygen. So why not? Okay, let's balance hydrogen. So if I put 4 hydrogen, so 4 H2O, it becomes 8 hydrogen. So hydrogen is balanced. Now how much is oxygen? 3 to the 6 plus 4, 10. So if I put a 5 here, it's balanced. So the first step is balance the chemical reaction. Now, so what does this mean? This means 1 mole of propane is combining with 5 moles of oxygen to form 3 moles of carbon dioxide and 4 moles of H2O. Now moles can be, for short, can be written as MOL. Okay. Now the question is, volume of oxygen needed at STP when 20 grams of propane are burnt. So 20 gram of propane is given. Now can I just go from mass to volume or mass to mass or even mass to moles or something else? No. We'll have to convert this to moles. Now how to convert this to moles? Remember the formula. Total moles is total mass divided by molar mass. The other thing that I also want to write right away is total moles. This is for ideal gases at STP, is total volume divided by molar volume. Now molar volume at STP is 22.4 liters, that is unknown for all ideal gases. Okay, we'll have to convert this mass into how many number of moles of propane is being burned. How do we do that? We can use this formula. Total moles is total mass by molar mass. So total mass is 20 grams and molar mass of propane is 3 times 12 plus 8 times 1. Okay, so how much is that? That is 20 divided by 36 plus 8, which is 44, or we can write 5 by 11. So this is number of moles of propane that is being burnt, right? So if 5 by 11 moles of propane is being burnt, how many moles of oxygen is being consumed? 1 mole needs 5 moles. So 5 by 11 will need 5 times 5 by 11, or this is 25 by 11 moles of oxygen is needed. Okay. Similarly, 1 mole produces 3 moles of carbon dioxide. So how many will 5 by 11 moles produce? 3 times 5 by 11, which is 15 by 11 moles of carbon dioxide, and 1 mole produces 4 moles of water. So 4 times 5 by 11 moles, or 20 by 11 moles of water are being produced. Now we have number of moles of oxygen, okay, that are needed. So now we can use this formula. Total volume is total moles times molar volume. So volume needed, total volume is number of moles 25 by 11 times 22.4 liters. So the answer is 50.9 liters of oxygen. Okay, so this is 50.9 liters. Okay, mass of water produced. So total mass is total moles times molar mass. So mass of water produced is number of moles of water produced 20 by 11 times molar mass of water. What is molar mass of water? We know 16 plus 2 is 18. So many grams. How much is that? So this is 32.7 grams. Okay, last question. Number of moles of oxygen atoms in carbon dioxide produced. So carbon dioxide produced is 15 by 11 moles. Now there is 2 moles of oxygen atoms in 1 mole of carbon dioxide. So then it follows that number of moles of oxygen atom is 15 by 11 into 2 moles of oxygen atoms, which is 30 divided by 11. So the answer is 2.7 moles. Okay. Now let's look at number 2. Now this one, let's rewrite the chemical reaction one more time. CaCO3 is giving us calcium oxide plus carbon dioxide. Now this equation is already balanced. Now the question we have is 50 grams of calcium carbonate is being heated. So this is all 1 mole, giving 1 mole of calcium oxide and 1 mole of carbon dioxide. Now 50 grams of calcium carbonate is being heated. Let's convert this into moles. So how much is that? Total mass divided by molar mass of calcium carbonate. Now calcium is 40, carbon is 12, and oxygen is 16. So 3 times 16. So how much is this? 40, 52 and 48. So 50 divided by 100 So 0.5 moles. So it's simple. 0.5 moles will produce 0.5 moles of CaO and 0.5 moles of carbon dioxide. Now question is, find volume of carbon dioxide produced at STP. So total volume is total moles times molar volume. So total moles is how much? 0.5, and molar volume at STP of any ideal gas is 22.4 liters. So the answer is 11.2 liters. Okay, now let's look at the last question here. So calcium nitrate, CaNO3 twice, when heated gives calcium oxide plus nitrogen dioxide plus oxygen. First thing is we need to balance the equation. So 2, 4, so 4 nitrogen. The oxygen is balanced now. 8, 9, 10, 11, 12, 3 to the 6, 6 to the 2. Okay. So now this is balanced. Now, so it follows 2 moles of calcium nitrate makes 2 moles of calcium oxide and 4 moles of NO2 and 1 mole of oxygen. Perfect. So it says if 5.6 liters of nitrogen dioxide is produced at STP, so 5.6 liter of nitrogen dioxide is produced. So total volume is given. Let's find out. So the total molar volume at STP is 22.4. So total moles of nitrogen dioxide produced is 5.6 divided by 22.4, and this is 0.25 moles. Perfect. So what was mass of calcium nitrate that was heated? So if 4 moles of NO2 is produced when 2 moles of calcium nitrate is heated, 1 will produce how much? 2 by 4 or half, and 0.25 will produce how much? So 2 by 4 times 0.25. So half of 0.25 is 0.125 moles of calcium nitrate. Now the question is, what was the mass of calcium nitrate? So total mass is molar mass times total moles. So from this we can write total mass is number of moles times molar mass. Now what is the molar mass of calcium nitrate? 40 plus nitrogen, we have 2. Nitrogen's atomic mass is 14. So 14 times 2 is 28. And oxygen we have 6. Oxygen's atomic mass is 16. So this is 96. How much is this? This is 164 grams per mole. So once you multiply this with the number of moles, it is 20.5 grams. So the answer to this one is 20.5 grams. This final problem that we'll solve is a little different, so pay attention carefully. Okay, so it says at 300 Kelvin and 1 atmospheric pressure, 10 milliliter of a hydrocarbon needed 55 milliliter of oxygen for complete combustion, producing 40 milliliter of carbon dioxide. Okay. The hydrocarbon is, I'll give you 4 choices: C4H2Cl, B, C4H6, C, C4H10, and D, C4H8. Okay, so how do we solve this? So let's assume the hydrocarbon is CXHY. Okay, and it is combining with oxygen to produce carbon dioxide and water. Okay, so the first thing is we need to balance this equation now. So let's put X here. So carbon has X, hydrogen has 2Y. So we need to do 2X here. So we need to put 2 here. Okay. So now carbon is balanced, hydrogen is balanced. Now what about oxygen? Oxygen is 4X plus Y. So what we need to do is we multiply this one more times with 2. So 4, and let's make this 4X, and we multiply this by 2Y. So now carbon is balanced 4X, hydrogen is 4Y, oxygen is 8X plus 2Y. So we can write 4X plus Y. So that gives you 8X plus 2Y. Okay. So now the equation is balanced. Now, so what is given? Let's write what is. So what we can infer from here, it means 4 moles of the hydrocarbon requires 4X plus Y moles of oxygen to produce 4X moles of carbon dioxide and 2Y moles of water. Okay. Now what is given is 10 milliliter of hydrocarbon is produced, hydrocarbon is burnt, and 55 milliliter of oxygen is required, producing 40 milliliter of carbon dioxide. Now, although this is not an STP, but for ideal gases, can we use Charles' law, which is V by T is a constant, right? 1 atmosphere at STP, pressure is 1 atmosphere, so that is same, and temperature is 273 Kelvin. So from that we can say molar volume at 300 Kelvin by 300 is molar volume at 273 Kelvin by 273, which which is 22.4 by 273. So we know the molar volume at 300 Kelvin is 22.4 times 300 by 273 liters. But we may not need to calculate this and use this, because let's assume this as V, okay? Because to find the number of moles from here, all we can do is given total volume divided by the molar volume. Same thing, so that is the number of moles. Same thing here, 55 divided by the molar volume. And this one we can say 40 divided by the molar volume. Okay. Of course, we are assuming here that the hydrocarbon is a gas, since the volume is involved, and we are assuming all gases are ideal gases. Okay. Now, so now 4 moles. Okay, let's look at this. So 4 moles of CXHY produces 4x moles of CO2. Okay, so 1 mole will produce how much? X moles of CO2, right? So 10 by V will produce how much? 10x by V of CO2. Okay. Now CO2. Okay. One other thing we can say is four moles of CXHY needs 4x plus y moles of O2. So 1 will need how much? 4x plus y divided by 4. And 10 by V will need how much? 4x plus y divided by 4 times 10 by V moles of O2. Okay. Now if you see, we have moles of carbon dioxide and moles of oxygen. So moles of carbon dioxide is 40 by V. So we can equate 10x by V equals 40 by V. And we can equate 4x plus y by 4 times 10 by V equals, how many moles of carbon oxygen is needed? 55 by V. Okay. So from this we know x is equals to 4, and from this we know we can cancel out 2, 5, 5, 11. So 4x plus y is 22. Now x we already know is 4. So y equals 22 minus 4x, 4 for the 16 is 6. So now we know x and y. So the hydrocarbon is C4H6. So the correct answer is B. Okay. So these are all the problems in stoichiometry using the mole concept, and pretty easy to solve actually, but you can potentially get a lot of questions from this subject in your entrance examinations. Easily you can score good in this subject. Okay. With that, good luck and cheers.